in the profound, silent darkness where our solar system dissolves into the interstellar void, two colossal worlds drift in a state of eternal twilight. They are the cerulean ghosts of our cosmic neighbourhood, Uranus and Neptune, twin titans painted in hues of impossible blue. Seen from afar through the patient lenses of our telescopes, they present an image of ethereal calmness, of serene and frozen majesty. Their atmospheres, a placid swirl of sapphire and aquamarine, seem to whisper of a peace that has lasted for billions of years. But this tranquility is a grand illusion, a beautiful lie that conceals a core of unimaginable violence and a secret of breathtaking extravagance. Beneath those placid cloud tops, in the crushing depths of their gaseous oceans, a process is unfolding that defies every terrestrial intuition we hold. It is a storm not of water nor of ice, but of something far harder, far more precious, a relentless glittering hail of diamonds. Solid, crystalline carbon, forged in a planetary crucible and raining down through the darkness for millennia, settling into a thick shimmering layer wrapped around their cores. This isn't science fiction. This is not a poet's dream. This is a scientific hypothesis that has clawed its way from the fringes of theoretical physics into the realm of startling possibility. And it forces us to ask a question so profound it borders on the absurd. How, in the coldest, most distant reaches of our solar system, can it rain the most coveted jewel on Earth? How is it truly possible? The very idea seems to revolt against the laws of nature as we know them. Diamonds, for us, are symbols of permanence, forged deep within our own world under the duress of immense heat and pressure. They are born of fire and geologic time, yet Uranus and Neptune are the ice giants, a name that evokes images of absolute unending cold. The tops of their clouds register temperatures of -224 degrees Celsius, a cold so severe it can freeze nitrogen solid. It is a cold that should extinguish any fire, a cold that should forbid the very chemistry of creation. How can a forge burn bright in the heart of a planetary freezer? This is the first, and perhaps most profound, paradox we must confront. To answer it, we must peel back the layers of these worlds, descending through their atmospheres on a journey of imagination, guided by the light of scientific discovery. The cold we measure is only skin deep. It is the temperature of the outermost veil of their atmospheres, the part that touches the vacuum of space. As we plunge deeper, a dramatic transformation begins. The pressure, gentle at first, begins to build with terrifying speed. We pass through layers of hydrogen, helium, and methane gas, the very air becoming thicker, heavier, a soupy mix that is neither gas nor liquid but something in between. Thousands of kilometers down, the weight of the entire world above begins to assert its dominance. The pressure mounts to hundreds of thousands, then millions of times the atmospheric pressure on Earth. It is a compression so extreme it is difficult for the human mind to grasp. Imagine the pressure at the bottom of our deepest ocean trench, the Mariana Trench. Now multiply that by 1,000,000. This is the realm we are entering. Under this cosmic vise, the laws of chemistry begin to warp and break, and as the pressure skyrockets, so too does the temperature. The planet's frigid exterior is a thermal blanket trapping the primordial heat left over from its violent formation 4.5 billion years ago. The core itself, a small rocky heart, radiates a fierce heat, cooking the layers above it. Deep within Uranus and Neptune, the temperature soars to thousands of degrees Celsius, hotter than the surface of some stars. Here, in this hidden inferno, we find the first part of our answer. The ice giants are not cold all the way through. They are worlds with a heart of fire wrapped in a shroud of ice. But heat and pressure alone are not enough. A diamond is a very specific thing. It is pure carbon, arranged in a perfect interlocking crystal lattice. To make them, you need a vast and ready supply of carbon atoms. Where could it possibly come from, in worlds primarily composed of hydrogen and helium? The answer lies in their beautiful blue colour. That mesmerising azure hue is not from water, as it is on Earth. It is the signature of methane gas in their upper atmospheres. Methane, a simple molecule with the chemical formula CH4, is one carbon atom bonded to 4 hydrogen atoms. It is the C in CH4 that provides the crucial ingredient for our cosmic jewels. As we continue our descent, reaching a depth of perhaps 8,000 kilometers, we enter the diamond rain zone. Here, the conditions are unlike anything on Earth. The pressure is more than 6 million times what we experience, and the temperature is a blistering 5,000 degrees Celsius. In this extreme environment, the methane molecules can no longer hold themselves together. The crushing force and searing heat act like a celestial blowtorch, violently tearing the molecules apart. The bonds between the carbon and hydrogen atoms are ripped asunder. The lightweight hydrogen atoms, freed from their carbon anchors, float upwards, while the heavier carbon atoms, now liberated and alone, begin to find each other in the dense superheated fluid. They are squeezed together with a force so immense that they have no choice but to link up, forming the strongest chemical bond in nature. They crystallize. They become, atom by atom, tiny solid diamonds. At first, they are mere specks, nanodiamonds glittering in the dark. But as they begin their long, slow fall toward the planet's core, they grow. Like hailstones accumulating ice as they fall through a terrestrial thundercloud, these diamond seeds attract other carbon atoms, growing larger and larger. A gentle shower becomes a torrential downpour, a cosmic hail of microscopic, then macroscopic diamonds, sinking through the dense mantle for thousands upon thousands of years. This incredible journey ends at the planet's core. Over geologic time, this relentless rain of treasure has likely formed a solid layer of diamond many thousands of kilometers thick, a celestial hoard of unimaginable size wrapped around the rocky heart of the planet. It is a vision that transforms these distant worlds from simple balls of gas into something far more exotic, far more dynamic. A planet with a diamond mantle. But to believe in such a fantastical process, we need more than just a compelling theory. We need proof. And this is where our detective story truly begins. We cannot send a probe to drill into the heart of Neptune. The crime scene, the place where this incredible alchemy occurs, is forever beyond our physical reach. The clues were scattered not in fingerprints or witness statements, but in the subtle wobbles of a planet's magnetic field, in the faint emissions of its internal heat, and in the complex equations of high-pressure physics. For decades, the idea of diamond rain was a whisper in the halls of planetary science, a fantastical piece of speculation born from the complex computer models that tried to simulate these alien interiors. It was an elegant solution to several nagging mysteries about the ice giants, such as their strange magnetic fields and their unexpected thermal energy budgets. But a model is just a ghost of reality. It is a sophisticated guess. To turn that ghost into something solid, something we could trust, science had to accomplish an extraordinary feat. It had to build a piece of an ice giant's heart right here on Earth. Scientists had to become planetary forgers, recreating the hellish conditions of a world half a solar system away inside the protected confines of a laboratory. This quest would demand some of the most powerful technology ever created. It would require lasers capable of unleashing blasts of energy that, for a fleeting nanosecond, rival the power output of our entire planet's electrical grid. It would require anvils made from the hardest substance known to us, diamond itself, to crush microscopic samples with forces that mimic the weight of a world. It was a challenge to push matter to its absolute limits, to force it to reveal its secrets under duress. This journey from a wild hypothesis to a demonstrable reality is the core of our investigation. We will witness the brilliant, painstaking experiments that took the abstract mathematics of planetary cores and transformed it into flashes of light and microscopic, man-made diamonds. We will meet the scientists who dared to believe in such an outlandish idea and dedicated their careers to proving it. And as we follow their path, we will discover that the implications of their success stretch far beyond just Uranus and Neptune. If diamonds can rain down inside our own solar system's ice giants, what does that mean for the countless worlds like them that we are now discovering around other stars? Neptune-sized exoplanets are among the most common types of planets in our galaxy. If the physics are universal, then it is entirely possible that the most common form of precipitation in the cosmos is not water, but a shower of diamonds. We may live in a universe where worlds with diamond mantles are not the exception, but the rule. This realization forces us to reevaluate our place in the cosmos. We think of diamonds as rare, a geological fluke of our own planet's specific history, but perhaps it is Earth that is the anomaly. Perhaps carbon, under the immense pressures found inside the majority of planets, is destined to become diamond. The universe, it seems, may be far more opulent, far more strange than we ever dared to imagine. This isn't just a story about a weird weather phenomenon on a distant planet. It is a story about the fundamental nature of matter. By recreating these extreme states, we are not just learning about other worlds, we are learning about the very rules that govern the existence of everything. We are writing a new chapter in the Encyclopedia of Physics, one that describes how atoms behave when they are pushed to the brink. What we are about to uncover is a testament to human curiosity, a story of how we can reach out across billions of miles of empty space to touch the impossible. It is an exploration of a process so alien it challenges our definition of a planet, a storm so valuable it makes all the treasures of Earth seem insignificant. Join us as we descend into the beautiful, violent hearts of the ice giants. The diamond rain is about to begin. How can a world composed of the most common ingredients in the universe, water, methane, ammonia, become a realm of unimaginable treasures, a factory for jewels larger than any human has ever held? This is the paradox of the outer solar system, a question that begins not in a laboratory, but in the deep, silent cold, nearly 3 billion kilometers from the warmth of our sun. Here, in the twilight zone of our cosmic neighborhood, drift two enigmatic worlds, Uranus and Neptune. For centuries they were little more than faint ghostly apparitions in our telescopes, distant cousins to the colossal gas giants, Jupiter and Saturn. We gave them a family name, lumping them together as a single class of planet. But this was a profound mistake, a simplification born from distance. It was an error that obscured a reality far more bizarre, far more alien, and far more brilliant than we could have ever conceived. To truly understand the possibility of diamond rain, we must first unlearn what we thought we knew. We must journey back to a time when these worlds were just points of light, and follow a trail of discovery that would slowly, painstakingly, peel back the layers of two of the most mysterious planets we've ever encountered, revealing that they are not gas giants at all. They are something else entirely. They are the ice giants. The term gas giant paints a simple, elegant picture. A colossal sphere of hydrogen and helium, a star that never quite ignited, with perhaps a tiny rocky core buried under an immeasurable atmosphere. For Jupiter and Saturn, this description holds true. They are titans of gas, capturing the primordial material from which the solar system itself was born. But as we cast our gaze further out to the placid turquoise of Uranus and the violent sapphire of Neptune, this familiar model begins to disintegrate. These worlds are fundamentally different creatures. While they do possess thick atmospheres of hydrogen and helium, this gaseous shroud is just that, a shroud. It is a relatively thin veneer concealing the true substance of the planet. The vast bulk of Uranus and Neptune, their very heart and soul, is made of heavier materials, the so-called ices. Now, when planetary scientists say ice, they don't simply mean the frozen water you find in your freezer. They are referring to a broader class of chemical compounds known as volatiles. These are molecules like water, yes, but also ammonia and methane, substances that are common in the cold, outer reaches of a solar system and which freeze at much lower temperatures than rock or metal. Think of it this way. Jupiter and Saturn are like cosmic balloons, inflated with the lightest elements in existence, their compositions mirroring that of the Sun. They are more than 90% hydrogen and helium by mass. Uranus and Neptune, by contrast, are more like celestial oceans, deep and dense. Their bulk is dominated not by gas, but by a strange, high-pressure soup of these ices. Less than 20% of their mass is hydrogen and helium. The rest, the overwhelming majority, is a churning exotic mantle of water, methane and ammonia, compressed to densities and temperatures that defy earthly intuition. This compositional chasm is the single most important distinction in the outer solar system. It is the master key that unlocks every other mystery these planets present, from their peculiar magnetic fields to the very weather raging across their cloud tops. This distinction wasn't born from a single dramatic discovery, but was pieced together over centuries of patient observation, each new piece of evidence chipping away at the old, inadequate gas giant label. It began with the simple act of weighing them, of calculating their density by observing the gravitational pull they exerted on their moons. The numbers that came back were puzzling. They were far denser than Saturn, far more substantial than a simple ball of hydrogen would suggest. There had to be something heavier inside, a massive reservoir of these cosmic ices, accounting for the extra gravitational heft. The light reflecting from their atmospheres offered another clue. The distinct blue-green hues of these worlds are not arbitrary. They are a chemical fingerprint, the direct result of the methane gas in their upper atmospheres absorbing red and orange light from the sun and reflecting the blues and greens back into space. The sheer depth of this colour told us that methane wasn't just a trace element. It was a significant player, a signpost pointing to the vast methane-rich interior hidden below. The old family portrait of the outer planets was wrong. We had mistaken distant cousins for identical twins. Jupiter and Saturn were one kind of world, but out here, in the dim frontier, a new class of planet was slowly coming into focus, a class defined not by gas, but by these strange, pressurized ices. Our journey to this realization begins in darkness, in the pre-industrial night of 1781. You are William Herschel, a musician and astronomer, peering through a homemade telescope from the garden of your home in Bath, England. You're meticulously charting the stars, a painstaking process of mapping the heavens. But on one particular night, you notice something amiss. Among the fixed, glittering points of light, one seems different. It's not a sharp pinprick like a star. It's a tiny, fuzzy, greenish disk. Night after night you return to it watching, and you see it move. It is not a star. Your first thought is that it must be a comet, a hazy wanderer passing through our cosmic backyard. But its path is too slow, too orderly, too majestic. You're not looking at a nearby visitor. You've stumbled upon something monumental, something that shatters the classical conception of the cosmos held since antiquity. For the first time in known history, a human being has discovered a new planet. You have found Uranus, and in doing so you have just doubled the size of the known solar system. For millennia, humanity's map of the planets ended at Saturn. Now, suddenly, there was a new frontier. But this frontier was frustratingly vague. Even with the best telescopes of the 18th and 19th centuries, Uranus remained a featureless aquamarine enigma. We could measure its orbit, estimate its size, but its true nature remained a complete mystery, a silent, ghostly sentinel in the void. The discovery of this new world, however, set in motion a chain of events that would lead to an even more profound revelation. As astronomers tracked the slow, stately orbit of Uranus, they noticed something was wrong. The planet was straying from its predicted path. It was being pulled, tugged by the gravity of something unseen, something lurking even further out in the darkness. It was a gravitational whisper from an unknown world. This celestial puzzle captivated two brilliant minds in the 1840s, John Couch Adams in England and Urbain Le Verrier in France. Working independently, armed with nothing but mathematics, pen and paper, they embarked on one of the most audacious acts of scientific prediction ever attempted. They sought to calculate the position of this phantom planet, to pinpoint its location in the sky, based solely on its subtle, gravitational influence on Uranus. It was an act of celestial cartography on a scale previously unimaginable. Le Verrier, completing his calculations first, sent them to the Berlin Observatory. On the very first night of their search, September 23, 1846, astronomers Johann Galle and Heinrich D'Arrest pointed their telescope to the coordinates Le Verrier had provided. And there it was, a tiny blue dot, almost exactly where the laws of physics predicted it would be. They had discovered Neptune. It wasn't found through a lucky glance, but through the pure power of scientific theory. Humanity had reached out into the void with mathematics and found a new world. Yet, like Uranus, Neptune was a mystery. It appeared as an even smaller, deeper blue disk, offering no clues as to its character. For more than a century and a half after their discoveries, these two planets would remain little more than tantalizing secrets. They were the last known worlds, the distant gatekeepers of our solar system, their true faces veiled by unimaginable distance. We knew they existed, we knew their orbits, but we didn't truly know them. What were they made of? What did their surfaces, if they even had surfaces, look like? What secrets were churning in their deep, dark hearts? Answering these questions would require more than just bigger telescopes. It would require us to leave our world behind, to send a robotic emissary on a grand journey into the darkness. That emissary was Voyager 2. Launched in 1977, it was a marvel of human ingenuity, a compact ambassador of science on a mission of unprecedented ambition. Its grand tour of the outer solar system was designed to take advantage of a rare planetary alignment, a gravitational slingshot opportunity that would only occur once every 176 years. After its triumphant encounters with Jupiter and Saturn, Voyager 2 sailed onward, alone, into the silent sun-starved abyss that lay beyond. For 7 long years, it coasted through the void, heading for a world no machine had ever visited. In January of 1986, it finally arrived. Its target, Uranus. The scientific community held its breath. Decades of speculation were about to be put to the test. What marvels would we see? Would there be swirling bands like Jupiter? A great storm? The first images that trickled back to Earth were, at first, an anticlimax. They revealed a world of almost perfect, placid beauty. Uranus was a serene aquamarine pearl, a sphere of pale, featureless blue-green. There were no raging storms, no dramatic cloud belts. It was eerily calm, almost inscrutable. But as Voyager 2 drew closer, this serene facade began to reveal its underlying strangeness. The probe confirmed something that astronomers had long suspected from faint ground-based observations. Uranus is a world knocked on its side. Its rotational axis is tilted by a staggering 98 degrees relative to its orbit. While other planets spin like tops as they circle the Sun, Uranus rolls like a ball, its poles alternately pointing directly at the Sun for decades at a time. This bizarre orientation suggests a cataclysmic impact deep in its past, a collision with an Earth-sized protoplanet that literally knocked the world over. The sideways planet was just the first of many puzzles. As Voyager 2 swept past, its magnetometers took the first ever readings from within the Uranian system, and what they found was deeply weird. Every other planet with a magnetic field has one that is roughly aligned with its axis of rotation, generated by a conductive fluid core, a kind of planetary dynamo. Uranus's magnetic field was a mess. It was tilted by a shocking 59 degrees from its rotational axis, and it wasn't even centered on the planet's core. It was offset by a third of the planet's radius, as if the engine generating it was sloshing around, far from the center. This was a monumental clue. A magnetic field this chaotic could not be generated by a simple, solid core like Earth's, or a metallic hydrogen core like Jupiter's. It had to be originating from somewhere else, from a shallower, stranger layer within the planet. The data pointed to a churning, slushy mantle of those compressed ices, water, ammonia, and methane that had become so pressurized they acted like a conductive fluid. For the first time, we had physical evidence that the ice giant model was correct. The heart of Uranus was not gas, nor was it rock. It was a bizarre, electrified ocean of slush, hidden beneath the tranquil blue-green clouds. The encounter was brief, just a fleeting flyby. But in those few short hours, Voyager 2 transformed Uranus from a distant point of light into a real physical place, a tilted, magnetically scrambled and profoundly mysterious world. As the probe receded, leaving Uranus to its solitary sideways journey, it carried with it a new set of questions that would set the stage for its final planetary encounter. The mystery of the ice giants had only deepened. 3.5 years later, in August of 1989, Voyager 2 braced for its final act. It was approaching Neptune, the last stop on its grand tour, a world even more distant and more mysterious than Uranus. Given the calm, almost featureless face of Uranus, scientists expected Neptune, colder and further from the Sun's energy, to be even more placid. They could not have been more wrong. The first images of Neptune were a stunning revelation, a spectacle of violent azure beauty. This was no serene pearl. This was a sapphire beast. The planet was a vibrant deep blue, streaked with gossamer-thin, high-altitude clouds of frozen methane ice, casting long shadows on the cloud decks below. And dominating its southern hemisphere was a monstrous cyclonic storm, a swirling vortex of unimaginable scale, immediately nicknamed the Great Dark Spot. It was a tempest as wide as the Earth itself, with winds screaming at over 2,000 kilometers per hour, the fastest sustained winds ever recorded on any planet in our solar system. The contrast with Uranus was jarring, almost nonsensical. Here were two worlds of similar size, similar mass, and similar composition. Yet one was placid and quiescent, while the other was a raging dynamic cauldron of atmospheric violence. Why? The answer, we now believe, lies deep inside. Neptune, for reasons we still don't fully understand, radiates more than twice the energy it receives from the distant Sun. It has a potent internal heat engine, a furnace in its core that churns its interior and powers its ferocious weather. Uranus, on the other hand, is strangely cold, radiating almost no excess heat at all. It is a world that has, for some reason, lost its inner fire. Just as it had at Uranus, Voyager 2's magnetometer delivered another shock as it plunged through Neptune's magnetic field. The field was just as bizarre, just as chaotic. It was tilted 47 degrees from the rotational axis and was again dramatically offset from the planet's physical centre. This was the corroborating evidence scientists needed. This couldn't be a coincidence. Two planets, two wildly offset magnetic fields. It was a clear, unambiguous signature of a shared interior structure, a confirmation that these two worlds were indeed a distinct class of planet, forged from the same icy materials. Their magnetic fields weren't born from a metallic core, but were generated within that vast, turbulent mantle of super-pressurized water, ammonia, and methane. The Voyager 2 flybys were our first fleeting introduction to the ice giants. They were a reconnaissance mission that raised far more questions than it answered. They revealed two sibling worlds, twins in composition but starkly different in personality. They showed us the sideways planet and the stormy planet. They gave us our first glimpse of their faint, delicate rings and their captured icy moons. Most importantly, they provided the first concrete data pointing to the extreme conditions lurking beneath their clouds. The combination of their massive gravity and their internal heat creates a universe of physics unlike anything on Earth. Deep within those blue atmospheres, the pressures mount to millions of times that of our own, and temperatures climb to thousands of degrees Celsius. The placid exteriors we see are just a veil. Below lies a realm where water is no longer a liquid we recognize but a supersonic fluid, and where methane, a simple gas in our world, is squeezed by unimaginable forces. The Voyager mission gave us the blueprint. It established the composition and hinted at the insane pressures and temperatures inside. It provided the foundational evidence, the initial spark of curiosity that led scientists back to their laboratories on Earth, asking a new, audacious question. What happens to methane, a molecule made of carbon and hydrogen, under the crushing, hellish conditions that must exist in the heart of an ice giant? The answer to that question would be the beginning of an incredible story. A story of chemistry so exotic, it borders on alchemy. A story that suggests that deep inside these distant blue worlds, it is raining diamonds. Those tantalizing threads of data, transmitted across the void by a fleeting Voyager probe, were not answers. They were cosmic provocations, echoes from an abyss we could not physically enter. The strange, off-kilter magnetic fields, the unexpected warmth radiating from the cores of these frozen worlds, the peculiar chemistry of their upper atmospheres, these were the clues left at the scene of a profound planetary mystery. But to decipher them, to weave them into a coherent story, we had to do something audacious. We had to build a planet, not with rock and ice, but with mathematics and light, inside the silicon heart of a supercomputer. We had to venture where no probe could ever survive, descending through the crushing layers of a simulated world, guided only by the unwavering laws of physics. This journey begins not with a spaceship, but with a cascade of equations. Each one is a foundational pillar, a digital blueprint for recreating the immense forces at play thousands of kilometers beneath the serene blue cloud tops. You see, a planet like Uranus or Neptune isn't a simple, layered object like a piece of fruit. It is a dynamic, churning engine of unimaginable power, a realm where the very definitions of solid, liquid, and gas dissolve into ambiguity. Our terrestrial intuition, honed by the gentle pressures of one atmosphere, becomes a useless guide in this alien domain. So we gather every scrap of information we possess, the planet's mass, its radius, its spin, its thermal output, and feed them into the machine. These are the boundary conditions, the cosmic guardrails that keep our digital creation tethered to reality. Slowly, painstakingly, a world takes shape in the virtual realm. The first layer is the familiar one, a sprawling atmosphere of hydrogen, helium, and the critical ingredient, methane. In our models, we descend through this gaseous veil, watching the numbers on our screens climb at a terrifying rate. The pressure, the sheer physical force of the miles of gas above begins to mount. 10 atmospheres, 100, 1,000. The temperature climbs in lockstep, not from sunlight, which barely touches these depths, but from the trapped primordial heat of the planet's formation and the slow, inexorable squeeze of gravity itself. We are leaving the realm of weather and entering a domain of pure, brutal physics, where the universe's fundamental forces begin to warp and twist the nature of matter itself. Soon, we cross a threshold for which there is no earthly equivalent. The distinction between gas and liquid vanishes. We enter a bizarre, supercritical ocean, a fluid that is neither one nor the other, but possesses the properties of both. It flows like a liquid but has the density of one, yet it expands to fill any container like a gas. Imagine an ocean without a surface, a seamless, unending sea that grows ever denser, ever hotter, with every kilometre we plunge. Here, the pressure is no longer measured in atmospheres, but in a far more formidable unit, the gigapascal. 1 gigapascal is 10,000 times the air pressure you feel around you right now. It is the pressure found at the very bottom of our deepest ocean trenches, a force capable of crumpling a military submarine as if it were a paper cup. And in our simulated ice giant, we are just getting started. Our model pushes deeper into the planetary mantle. The numbers spiral into the realm of science fiction. 200 gigapascals, 500, 600. This is a pressure that exceeds the centre of our own Earth. It is a force so monumental, so utterly compressing, that it can rearrange the very architecture of atoms. It is a gravitational anvil, a relentless hammer pounding on everything within its grasp. The temperature, too, has become hellish, soaring to thousands of degrees Celsius, hotter than the surface of many stars. This is not the gentle warmth of a hearth. It is a violent, chaotic thermal energy, a thermodynamic blowtorch that agitates every single molecule, trying to rip it apart from its neighbours. It is here, in this simulated crucible of unimaginable extremes, that we turn our attention to methane. On Earth, methane, CH4, is a simple, unassuming molecule. 1 carbon atom bonded to 4 hydrogen atoms. It is the primary component of natural gas, a fuel we burn, a substance whose behaviour we understand intimately. In the upper atmosphere of Uranus and Neptune, it plays the role of a celestial artist, absorbing red light and reflecting the brilliant blues and azures that give the ice giants their captivating beauty. For decades, we assumed its role ended there. We pictured it mixing into the deep interior, perhaps dissolving into the supercritical fluid, but remaining fundamentally unchanged, a simple passenger on a journey to the planet's core. But our models, governed by the unforgiving logic of chemistry and physics, began to tell a different, far more violent story. They began to scream that in this inferno nothing remains a passenger. Everything becomes fuel for a bizarre form of planetary alchemy. Under hundreds of gigapascals of pressure, and at temperatures reaching 5, 6, even 7,000 degrees, the humble methane molecule is pushed past its breaking point. The 4 covalent bonds holding the hydrogen atoms to the central carbon atom, bonds forged in the stellar nurseries of the early solar system, can no longer withstand the strain. The relentless pressure squeezes the molecule from all sides, while the furious thermal energy vibrates it with increasing violence. Think of it as a bell being struck by a hammer, a gentle tap and it rings, but strike it with enough force, again and again, and the metal itself will shatter. This is the fate of methane in the deep interior. The bonds are not merely stretched, they are annihilated. The molecule is violently disassembled. In a process known as pyrolysis, the methane quite literally cracks apart. The carbon and hydrogen atoms, once locked in a stable, predictable embrace, are divorced. They are liberated into the swirling, ultra-dense fluid, a chaotic soup of independent particles. Suddenly the mantle is no longer a simple mixture of hydrogen, helium, and methane. It has become a reactive chemical cauldron. We have an environment flooded with free hydrogen atoms and, most critically, a vast population of newly single, unbound carbon atoms. This is the pivotal moment in our theoretical journey, the instant the entire chemistry of the planet's interior is rewritten. The model showed this wasn't a rare or fringe event. It was an inevitable consequence of the conditions. A significant fraction of all the methane that sinks into the mantle must undergo this brutal transformation. What happens next is a cascade of creation born from destruction. Nature, even in this alien hellscape, abhors a vacuum of chemical stability. These newly liberated, highly reactive atoms immediately begin searching for new partners. The hydrogen, being the lightest and most abundant element, mostly finds other hydrogen atoms, pairing up to form stable H2 molecules, enriching the vast hydrogen ocean that constitutes the bulk of the planet. But the carbon is different. It is a uniquely versatile element, with an innate talent for building complex structures. In the churning chaos of the mantle, a lone carbon atom is a powerful agent of creation. It will not remain alone for long. Our simulations tracking the interactions of trillions of virtual particles show us the next step in this dramatic sequence. Carbon atoms, finding each other in the dense fluid, begin to link up. At first, they form simple chains, recreating more complex hydrocarbons, fleeting phantoms like ethane and propane, which are themselves immediately torn apart by the ferocious heat and pressure. This is a false start, a temporary reunion before an even more profound transformation. The conditions are simply too extreme for these larger, more fragile molecules to survive. The universe is pushing the carbon toward a far more stable, far more permanent configuration. The ultimate destiny for these atoms is not to bond with hydrogen, but to bond only with themselves. As the carbon atoms are stripped of their hydrogen partners, they begin to cluster together, forming what we might recognize as microscopic grains of soot. An elemental darkness begins to permeate the supercritical fluid. Imagine a slow, dark rain of pure carbon, precipitating out of the surrounding ocean like snowflakes in a winter storm. This is not the familiar fluffy soot from a candle flame. This is carbon forged under pressures that can alter atomic structures, creating dense, complex allotropes. The initial fallout might be amorphous, a disordered jumble of atoms, or it might take the form of graphite, the same stable carbon structure found in the tip of your pencil with its familiar layered sheets. A rain of graphite, falling through a sea of supercritical hydrogen thousands of miles deep. Even this image is enough to stagger the imagination. But the journey is not over. The descent continues. This dark, carbonaceous rain falls deeper and deeper into the mantle, encountering ever greater pressures and ever higher temperatures. The forces continue to build, the gravitational anvil pressing down with a weight that is almost beyond comprehension. And it is here that carbon undergoes its most spectacular and final transformation. Graphite, with its planar, sheet-like structure, is stable and strong under terrestrial conditions. But under the titanic pressures of an ice giant's deep mantle, even graphite cannot hold its form. The universe has one final, more perfect, more indestructible configuration in mind for carbon. The pressure becomes so intense that it forces the carbon atoms out of their comfortable graphite sheets and compels them into a new, crystalline lockstep. Every single carbon atom is forced into a perfect tetrahedral lattice, forming a covalent bond with 4 other carbon atoms. Each bond is identical, incredibly short and phenomenally strong. This is not a sheet. It is a 3-dimensional interlocking cage of pure carbon, the most rigid and tightly bound structure that matter can assume. There is no longer any give, no possibility of shearing or compressing further. The carbon has achieved its ultimate state of density and stability. It has become diamond. The theoretical models were unequivocal. The conditions deep within Uranus and Neptune are not just suitable for the formation of diamonds, they are virtually perfect for it. The methane breakdown is not a hypothesis, it is a chemical inevitability. The subsequent formation of pure carbon is not a possibility, it is a direct consequence. And the final compression of that carbon into a crystalline diamond structure is the logical, staggering conclusion. The digital worlds we had built, born from cold equations and processing power, were now showing us a vision of almost mythic proportions. Not just a few diamonds, scattered like jewels in the rock. The models predicted a continuous, unending process, a ceaseless diamond rain where trillions of carats of freshly forged gemstones precipitate from the mantle and fall downwards through the planet's interior over thousands of years. These are not the tiny, flawed stones we mine on Earth. They are born in a uniform, high-pressure environment, likely forming into flawless, massive crystals. Some models suggested these falling diamonds could grow to be centimeters, perhaps even meters in diameter. We were forced to envision a dark, alien sea where shimmering mountains of pure diamonds slowly sink through the fluid depths toward the planet's core. This was a radical, almost unbelievable concept. It transformed our view of these planets from quiet, icy sentinels at the edge of our solar system into vast, active diamond factories. It suggested a dynamic carbon cycle on a scale we had never imagined, where the blue colour of the sky was inextricably linked to a tempest of gemstones in the abyss. The theory was internally consistent. It obeyed every known law of physics and chemistry. It elegantly connected the observed atmospheric composition with the mysterious internal heat source. This process of chemical differentiation and rainout would release enormous amounts of gravitational energy, helping to explain why these planets are warmer than they should be. The ghost in the machine was showing us a universe more wondrous and strange than we had ever dared to write in our fictions. Yet, for all its elegance and explanatory power, this remained a story told by shadows on a cave wall. It was a theoretical prediction, a phantom conjured within a supercomputer. No matter how compelling, a simulation is not proof. It is a signpost, a map pointing toward a treasure that may or may not be real. The sheer audacity of the claim demanded an equal audacity in seeking proof. We had built a planet in a machine and witnessed a miracle. Now we were faced with an even greater challenge. Could we replicate this cosmic forge, even for a billionth of a second here on Earth? Could we take this extraordinary theory out of the digital realm and make it real, right before our eyes? The quest for the diamond rain had to leave the world of simulation and enter the laboratory. For decades, this staggering vision of shimmering, sinking treasure remained confined to the silent world of code and computation. It was a ghost story told in the language of physics, a phantom haunting the digital models of our solar system's most distant worlds. The mathematics were elegant, the simulations compelling, but they were still just that, simulations. They offered a tantalizing glimpse into a reality we could never visit, a forecast for a bizarre weather system raging hundreds of millions of miles away. How could we ever truly know? How could we bridge the impossible gulf between a theoretical prediction and the undeniable truth? To answer that, we had to stop looking out at the planets. We had to turn our gaze inward to the cathedrals of science here on Earth and undertake one of the most audacious acts in the history of planetary exploration. We had to build a piece of a planet in a laboratory. The challenge was, to put it mildly, monumental. You cannot simply scoop up a bucket of Uranus's atmosphere and bring it home. The conditions we sought to replicate were so utterly alien, so far beyond any terrestrial experience, that they bordered on the absurd. We needed to generate pressures millions of times greater than the air you're breathing right now. We had to achieve temperatures that would make the heart of a volcano seem like a cool autumn breeze. We needed to compress matter until its very atomic structure buckled and broke, forcing it to reassemble into something new, something precious. It was a quest to recreate a planetary forge, to hold the heart of an ice giant in the palm of our hands, if only for a fraction of a second. This wasn't merely about mixing chemicals in a beaker. This was about wielding the fundamental forces of the universe on a microscopic scale. A symphony of destruction and creation orchestrated with breathtaking precision. Our first tool in this extraordinary endeavour seems, at first glance, like a paradox. To probe the creation of the universe's hardest known natural substance, scientists turned to that very same material. They built a device of exquisite power and simplicity known as a diamond anvil cell. Imagine taking two perfectly cut, flawless gemstones, diamonds chosen for their absolute purity, and grinding their tips into microscopic points. These two diamonds are then mounted in a powerful mechanical vise. Between their opposing tips, a space smaller than the width of a human hair, a minuscule sample is placed. A microscopic droplet of the primordial soup we believe fills the ice giants, a mixture rich in carbon and hydrogen. Then, with the slow, inexorable turn of a screw, the vise begins to close. The pressure builds. The force exerted by the human hand is magnified, concentrated onto that infinitesimal point where the two diamond tips meet. The pressure climbs past anything found in the deepest ocean trenches on Earth. It surpasses the crushing forces at the centre of our own planet. The molecules in the sample are squeezed, their bonds groaning under the strain, their atoms forced into an intimacy they would never naturally endure. As the pressure mounts to over 1 million atmospheres, the clear sample chamber becomes a window into another world, a tiny captive piece of a distant planet's mantle. Yet, pressure alone isn't enough to break the stubborn bonds of methane and initiate the cosmic alchemy we were searching for. For that, we needed fire. Not the fire of combustion, but a purer, more focused energy, a beam of light. Through the transparent diamond walls of the anvil, a laser is fired. For a brief moment, the trapped hypercompressed sample is superheated to thousands of degrees Celsius. It is here, in this microscopic crucible, under the simultaneous assault of unimaginable pressure and searing heat, that the magic is supposed to happen. The hydrogen atoms, battered and energized, are stripped away from the carbon. The carbon atoms, now orphaned and adrift in this violent, congested environment, find themselves with no other choice. They are shoved together, their electron shells overlapping, their very nature forcibly realigned by the laws of physics. They link up, forming the brutally strong tetrahedrally bonded lattices that are the unmistakable hallmark of diamond. The first hints of success were subtle, gleaned from the way light scattered off the transformed sample. The data suggested that something new, something incredibly dense and crystalline, was indeed forming inside the anvil. It was a monumental step, the first tremor of a paradigm shift. But to truly prove it, to capture the birth of a diamond in the act, we needed a bigger hammer. We needed a celestial blowtorch. We found it at places like the SLAC National Accelerator Laboratory in California, home to an instrument of truly epic proportions, the Linux Coherent Light Source, or LCLS. This is not a laboratory in the traditional sense. It is a 2-mile-long particle accelerator, a machine designed to manipulate electrons with near-light speed precision. Its purpose is to generate the world's most powerful X-ray laser, a beam of such intensity and focus that it allows us to watch chemical reactions unfold in real time, to take snapshots of atoms in motion. The LCLS is, in essence, the ultimate stop-motion camera for the molecular world. It was here, and at similar behemoths of science like the National Ignition Facility, that the quest for diamond rain would reach its stunning climax. The diamond anvil cell was about slow, sustained pressure. These facilities were about a single cataclysmic shock. The philosophy is different. Instead of squeezing a sample, you obliterate it with such focused power that, for a fleeting instant, the conditions of that impact perfectly mimic the descent into an ice giant's core. The target is a tiny piece of plastic, often polystyrene, no bigger than the head of a pin. It may seem mundane, but this simple plastic is made of long chains of hydrogen and carbon, a perfect solid-state stand-in for the methane slush we theorize exists deep inside Uranus and Neptune. This miniature world is placed at the heart of a vast target chamber, a spherical void bristling with diagnostics, sensors, and the focusing lenses of immensely powerful optical lasers. The chamber is a technological marvel, a temple built to witness a singular violent event. All the air is pumped out, creating a near-perfect vacuum. For in the world of high-energy physics, even a single stray molecule of air could disrupt the delicate choreography of the experiment. Then the countdown begins. Deep within the facility, colossal banks of capacitors begin to charge, whining with the strain of holding back city-level amounts of electricity. The energy gathers, a storm of electrons waiting to be unleashed. In the control room, a hushed silence falls. Scientists who have spent years planning for this single moment watch their monitors, their faces illuminated by the glow of data streams. Every sensor, every diagnostic must be perfectly calibrated. The timing must be accurate to within trillionths of a second. They are not just conducting an experiment, they are attempting to photograph a ghost, to catch a glimpse of a process that lasts for a shorter span of time than it takes light to cross a room. The final command is given. The capacitors discharge their biblical energies into the laser amplifiers. For an instant, a flash of light brighter than anything ever created on Earth erupts within the heart of the machine. Dozens of high-power laser beams focused down to a microscopic point all strike the tiny plastic target simultaneously. The impact is instantaneous and apocalyptic. The surface of the plastic vaporizes, turning into an exploding cloud of plasma that rockets outward. In accordance with Newton's third law, for every action, there is an equal and opposite reaction. This outward explosion creates an inward-moving shockwave of unimaginable force. This shockwave slams into the remaining plastic, compressing it with a violence that is difficult to comprehend. For a few brief nanoseconds, a tiny speck of matter within that chamber in California is subjected to the same hellish pressures and scorching temperatures that exist 10,000 kilometers beneath the placid blue cloud tops of Neptune. It is a moment of pure elemental transformation. The polystyrene's chemical bonds are not gently coaxed apart, they are shredded by the sheer violence of the shockwave. The carbon and hydrogen atoms are ripped from their molecular chains, creating a dense, hot, chaotic fluid. This is the critical moment, the instant of creation frozen in time. Would the carbon atoms simply disperse? Or would the crushing pressure, the very force that tore them apart, now slam them back together into a new and more exotic form? The entire event, from the laser strike to the target's complete disintegration, is over in less than the blink of an eye. There is no sound, no visible spectacle beyond the initial flash. The proof, the discovery, lies hidden in the deluge of data captured by the surrounding sensors. And this is where the genius of the LCLS X-ray laser comes into play. Timed with impossible precision, a burst of X-rays, unimaginably brilliant and infinitesimally brief, is fired through the target at the exact moment of maximum compression. This X-ray pulse acts as a cosmic flashbulb. It streams through the hyper-compressed matter and, as it does, it interacts with the atoms inside. If those atoms are arranged randomly, like in a liquid or a gas, the X-rays will scatter in a diffuse, unremarkable pattern. But if the atoms have organized themselves into a repeating crystalline structure, the X-rays will diffract. They will bounce off the neat rows and planes of atoms in a very specific, predictable way, creating a distinct pattern of bright spots and dark bands on the detector. It is a unique signature, an atomic fingerprint, and the scientists were looking for one specific fingerprint above all others, the unmistakable symmetrical pattern of diamond. The data pours into the computers. The control room is a sea of focused intensity as algorithms begin to sift through the terabytes of information from that single shot. They are searching for the signal amid the noise, the pattern hidden within the chaos of the explosion, and then it appears on the screen. Faint at first, but growing clearer as the data is processed. A series of concentric rings, dotted with bright, sharp spots. It is not the diffuse pattern of a liquid. It is the sharp geometric signature of a crystal lattice. They run the analysis, comparing the pattern to a library of known materials, the spacing of the rings, the angles of the spots. It is a perfect match. There is no ambiguity. No other interpretation is possible. For a few fleeting nanoseconds, inside that chamber, carbon atoms liberated from their plastic prison had been crushed together to form crystalline nanodiamonds. It was a moment of profound revelation, the kind of discovery that echoes through a scientist's entire career. The theory was no longer a theory. The ghost story was real. We had done it. We had captured undeniable empirical proof that under the conditions of an ice giant's interior, carbon atoms do indeed precipitate out of their chemical soup and crystallize. They don't form glittering cut gemstones as we might imagine. The experiment showed the creation of nanodiamonds, structures only a few thousand atoms across, far too small to be seen with the naked eye. But their size is irrelevant. Their existence is everything. It confirmed that deep within Uranus and Neptune, a constant gentle rain of these microscopic diamonds is likely falling through the dense, soupy mantle. A slow, steady drizzle of treasure accumulating over billions of years. The experiment was a triumph, a vindication of decades of theoretical work. By bringing a star to Earth, by forging a planet's heart in a vacuum chamber, we had solved a central piece of the puzzle. We now knew with certainty that diamond rain was not science fiction. It was a fundamental meteorological process on the giant frozen worlds at the edge of our solar system. And yet, as with all great discoveries, this stunning confirmation did not close the book on Uranus and Neptune. Instead, it ripped the book wide open, revealing chapters of even deeper and more tantalizing mystery. Proving that the diamonds exist was one thing. Understanding what they do to an entire planet is another question entirely. What happens to this endless shower of sinking crystals? How does a constant rain of diamond, a material that is both an excellent thermal conductor and an electrical insulator, sculpt the interior of a world? How might it power the strange, chaotic magnetic fields that had baffled us for so long? The laboratory had given us our answer, but in doing so it had thrown down a new gauntlet, pointing us toward an even more profound enigma that lay waiting in the deep, dark, diamond-filled hearts of the ice giants. The impossible had been made real. There, in the split-second inferno of the world's most powerful lasers, humanity had forged a diamond from the stuff of ice giants. That fleeting, microscopic speck of crystal, born under conditions mimicking the heart of Neptune, was more than just a scientific triumph. It was a key. For the first time, we held tangible proof that the universe was even more wondrous than we had dared to imagine. But proving a single raindrop can form in a laboratory is one thing. To truly comprehend the deluge, to witness the planet's sculpting power of a storm that has raged for billions of years, we had to go deeper. We had to leave the reassuring certainty of physical experiment behind and venture into a realm built not of matter, but of pure information. Our destination, a virtual Uranus, a ghost Neptune, meticulously constructed inside the silent humming mind of a supercomputer. This is the next great frontier of planetary science, an exploration conducted not with telescopes and probes, but with algorithms and petabytes of data. You cannot simply peel back the layers of a world like Neptune. The crushing gravity, the temperatures hotter than the surface of the sun, the truly alien states of matter, they form an impenetrable barrier. So, scientists build a digital twin. They feed the machine everything we know. The planet's mass, its radius, its atmospheric composition of hydrogen, helium and methane. They input the laws of physics, the complex equations that govern how elements behave under pressures millions of times greater than our own. From this mathematical seed, a world begins to coalesce in silicon. It is a painstaking process, a digital genesis that can take years, demanding more computational power than thousands of home computers combined. Inside this digital crucible, scientists can finally ask the question that the laser experiment left hanging in the air. What happens next? What is the life story of a diamond born in the churning depths of a gas giant's mantle? The simulation begins. We are 10,000 kilometers below the placid blue cloud tops, in a region of unimaginable hostility. Here, the primordial soup of hydrogen and helium gives way to a stranger ocean of water, ammonia, and methane, squeezed into a hot, dense fluid. It is here that the alchemical process, proven on Earth, begins on a planetary scale. The simulations show us that as methane molecules, simple structures of one carbon atom and 4 hydrogen atoms, are driven deeper by the planet's immense gravity, the bonds that hold them together are shattered. The hydrogen is stripped away, but the carbon atoms, now liberated and alone, are relentlessly compressed. They begin to find each other in the violent incandescent chaos. This is not a gentle crystallization. The virtual sensors of our simulation show it as a frantic, instantaneous process called nucleation. Clusters of just a few hundred carbon atoms, under the celestial hammer of 1 million atmospheres of pressure, are shocked into the rigid, perfect lattice of a diamond. They are born as nanoparticles, utterly invisible, yet they are the seeds of something immense. The simulation reveals a process of astonishing efficiency. Rather than remaining as a diffuse fog of carbon dust, these nascent diamond seeds become gravitational anchors. They immediately begin to sink, and as they fall, they grow. The surrounding fluid is still rich with free carbon atoms, and these atoms, drawn by powerful atomic forces, latch onto the falling crystals. It's a process akin to a snowflake gathering mass as it tumbles through a winter sky, but on a scale that defies terrestrial comparison. Our models, running forward through virtual millennia, show these specks of diamond dust growing into grains, then pebbles. Over thousands of years, they could accrete into crystalline boulders meters wide, perhaps even kilometers across, becoming what could only be described as diamondbergs. We are witnessing a cosmic snowstorm, a perpetual silent and incredibly heavy rain of pure carbon falling from the upper mantle toward the planet's mysterious core. This is no longer a theoretical curiosity. It is a fundamental geological process, a critical part of the planet's circulatory system, hidden from our eyes for all of history until now. The journey downward is a long and perilous odyssey through ever more exotic landscapes. As these diamonds descend, they leave the hot, dense fluid where they were born and enter a new layer, a region so alien it stretches the very definition of matter. Here, roughly 17,000 kilometers deep, the water, ammonia and methane exist in a supraeonic state. This is a phase of matter predicted by theory for decades, but only recently confirmed in laboratories, a substance that is both solid and liquid at the same time. Imagine a crystalline lattice made of oxygen atoms, locked into a solid structure like ice. But through this rigid, frozen framework, the hydrogen nuclei flow like a liquid, a sea of protons moving freely. It is a world of electrical currents and bizarre chemistry. And through this superionic ocean, our falling diamonds now plough. The simulations show them sinking at speeds of up to 9,000 kilometers per hour, glowing with the white-hot heat of their surroundings. They are like celestial anvils dropping through the heart of the world, unstoppable and unyielding. For millions, perhaps billions of years, this process has continued uninterrupted. A ceaseless, silent cascade of treasure accumulating at the bottom of the mantle. And this leads to the most staggering prediction to emerge from these digital worlds. What is the ultimate fate of this diamond rain? Where does it all end up? The models present us with a vision that borders on mythology. As the diamonds reach the deepest parts of the mantle, just above the rocky Earth-sized core, the pressure becomes so extreme, so astronomically high, that even the rigid structure of a diamond can be overwhelmed. Here, at the core mantle boundary, the simulation suggests the temperature can soar to over 7,000 degrees Celsius, while the pressure exceeds 10 million times that of Earth's atmosphere. Under these conditions, something extraordinary may happen. Diamond, the hardest substance we know, may begin to melt. The possibility is almost too fantastic to entertain. A liquid diamond ocean, a shimmering molten sea of carbon miles deep, sloshing atop the planet's solid core. Some models suggest this ocean could be vast, a global layer wrapping the core in a shell of liquid gem. Other simulations, favouring slightly different temperature and pressure gradients, predict a different fate. Instead of melting, the diamonds simply pile up. Over the eons, the relentless rain builds a solid layer, a crust of pure diamond hundreds, maybe even thousands of kilometers thick. Think of it. A stratum of the planet's geology composed of the most precious material on Earth, forming a bedrock of unimaginable size and value. Whether it is a liquid ocean or a solid shell, the implication is the same. The deep interiors of Uranus and Neptune are home to quantities of diamond that would dwarf all of Earth's known reserves combined. They are not just ice giants, they are carbon-rich jewel worlds, with treasures buried so deep we can only ever hope to glimpse them through the lens of physics and the ghost light of a supercomputer. But this incredible phenomenon is not just a geological curiosity. It is not just about the formation of a spectacular hidden treasure. The very existence of this diamond rain has profound consequences, reaching out from the depths to fundamentally alter the entire planet. It may in fact solve two of the longest-standing and most perplexing mysteries of the outer solar system. The first mystery is one of heat. Uranus is a cold, strangely inert world. It radiates almost no excess heat from its interior, barely more than it receives from the distant sun. It seems to be in a state of thermal equilibrium. Neptune, its near twin in size and composition, is wildly different. It radiates more than 2.5 times the energy it absorbs from the sun. It is a dynamic, storm-tossed planet with the fastest winds in the solar system, all powered by a vigorous internal heat engine. Why the dramatic difference between two such similar worlds? Diamond rain provides a compelling, elegant answer. As the incredibly dense diamonds form and sink, they are displacing the lighter hydrogen and helium around them. This process, known as gravitational differentiation, is a powerful source of energy. As the heavier material falls toward the center of gravity, its immense potential energy is converted into thermal energy, into heat. It's the same principle that heats a bicycle pump as you compress the air inside, but on a planetary scale that is difficult to fathom. The slow, steady rain of diamonds acts like a planetary furnace, continuously releasing heat into the interior. Our model suggests that on Neptune this process is still active and vigorous, churning its interior and powering its violent weather. The simulations for Uranus, however, paint a different picture. Perhaps its interior is stratified in such a way that the diamond rain has slowed or even stopped. Or maybe, over its long history, most of its available carbon has already rained out, leaving the planet in the cold, quiet state we see today. The diamond rain theory doesn't just explain a quirk, it potentially explains the very personality of each planet, Neptune's fury and Uranus's eerie calm. Yet, the most transformative implication of this internal blizzard may lie in its ability to unravel an even deeper enigma, a puzzle written in the language of magnetism. To understand it, we must remember that a planet's magnetic field is generated by a dynamo, a process requiring 3 ingredients: an electrically conductive fluid, a source of energy to stir that fluid through convection, and planetary rotation. On Earth, this dynamo operates in our molten iron core. But on Uranus and Neptune, the magnetic fields are utterly bizarre. They are not neat and tidy like Earth's, with poles roughly aligned with the planet's spin axis. Instead, they are wildly tilted. Uranus's magnetic field is offset by a staggering 59 degrees from its rotational axis. Moreover, the fields are not centered within the planets. They are significantly displaced, as if the entire magnetic dynamo is shifted to one side. They are also incredibly complex, with multiple north and south poles scattered across the surface. For decades, this magnetic chaos has been a source of intense debate. The conventional theory held that the dynamo must be operating in a thin, slushy shell of superionic water in the upper mantle, rather than deep in the core. But why would it be confined to such a shallow layer? The diamond rain simulations offer a breathtakingly new perspective. As these solid, electrically insulating diamonds plummet through the conductive, fluid layers of superionic water, they must be creating immense turbulence. They are not sinking gently, they are disrupting the very fabric of the mantle. Imagine millions of kilometers-wide boulders constantly churning the electrically charged fluid that generates the magnetic field. This celestial stirring would fundamentally alter the flow of material. It could prevent the formation of a simple, deep-seated dynamo like Earth's, and instead create a complex, chaotic and shallow one. The falling diamonds would act as giant, non-conductive impediments, forcing the conductive fluid to flow around them in turbulent, unpredictable patterns. This could explain everything: the extreme tilt, the off-center nature, the messy complexity of the fields we observe. The diamonds are not just a passenger on a journey to the core, they are the gravitational gyroscope, the planetary stirrer, the unseen hand that sculpts the invisible magnetic architecture of these worlds. We set out to understand a simple chemical reaction, the transformation of methane into diamond. We found a process that defines the very nature of a planet, a process that dictates its internal temperature, drives its weather, and forges its magnetic soul. The computer models have given us a window into this hidden realm, a vision of diamond seas and crystalline continents. They have transformed our view of Uranus and Neptune from simple balls of ice and gas into dynamic, evolving geological machines of incredible complexity. The ice giants are no longer the quiet, distant members of our solar family. They are active, powerful worlds, shaped by a process more commonly found in a jeweler's workshop than in the cosmos. And as we refine these simulations, a new, tantalizing question begins to emerge. If this can happen here, in our own backyard, what does it mean for the countless similar worlds we are now discovering across the galaxy? We are on the cusp of realizing that the universe may be filled with these diamond worlds, and that the story we have uncovered here is not an exception, but a cosmic rule. And so, in a flash of laser light within a laboratory on Earth, the final piece of the puzzle fell into place. What had once been a fantastical conjecture, a wild dream born from the sparse data of a distant flyby, was now grounded in empirical reality. The laboratory diamonds, microscopic and fleeting, were the confirmation we needed. They were the Rosetta Stone that allowed us to translate the language of our theoretical models, to understand the whispers we'd been hearing from the atmospheres of Uranus and Neptune for decades. With this key in hand, the scattered fragments of evidence, the atmospheric methane deficits, the strange internal heat signatures, the baffling magnetic fields, suddenly coalesce. They snap together, not as isolated curiosities, but as interconnected components of a single, breathtakingly elegant planetary engine. We can now, for the first time, step back and witness the entire majestic cycle, a process of cosmic alchemy that has been shaping these worlds for billions of years. The journey begins some 8,000 kilometers below the cloud tops, in a layer of the atmosphere where the pressure climbs to hundreds of thousands of times that of Earth at sea level. Here, in this crushing twilight zone, the abundant methane molecules which give the ice giants their serene blue hues can no longer withstand the strain. The immense pressures and rising temperatures, approaching thousands of degrees, act like a molecular vice. They violently shatter the chemical bonds holding the methane, CH4, together. The hydrogen atoms are stripped away, leaving the carbon atoms suddenly, furiously alone in a sea of superheated fluid. But in chaos, there is opportunity. Under these extreme conditions, isolated carbon atoms are an unstable anomaly. They seek stability, a stronger configuration, and the strongest, most stable structure that carbon can form is the tetrahedral lattice of a diamond. Atom by atom, they lock together, crystallizing directly out of the hot, dense fluid mantle. A jewel is born, not over geological eons in the crust of a rocky world, but in a furious instant within the heart of a gas giant storm. This is the moment of creation, the synthesis of all our observations. Our models predicted this exact pressure-temperature window for what scientists call diamond precipitation. The atmospheric data confirms that something is indeed removing carbon from the upper layers, explaining the observed methane depletion that has long puzzled us. And the laboratory experiments, recreating these very conditions, produced the nano-diamonds that proved the mechanism was not just plausible, but inevitable. We're no longer looking at disparate facts. We're witnessing an unbroken chain of evidence, a complete narrative from cause to effect. What begins as a simple molecule in the cold, distant sunlight culminates in the formation of a gemstone in the crushing dark. And its story has only just begun, because this newborn diamond does not remain suspended. It is substantially denser than the surrounding fluid mantle of water, ammonia, and other ices, and so it begins to fall. This is not a gentle, poetic rainfall. You must imagine a hailstorm of unimaginable scale and duration, a perpetual cascade of solid carbon sinking through a planetary interior. The diamonds may start small, but as they descend, they can grow, accreting more carbon atoms from the environment, potentially merging with other falling crystals. Over thousands of years, they could grow from microscopic specks to carats, to kilograms, to boulders of pure crystalline carbon miles wide. They sink deeper and deeper, a relentless gravitational pilgrimage toward the planet's core. And as they fall, they do something profoundly important. They perform a fundamental act of physics that alters the very destiny of their world. They convert gravitational potential energy into heat. Think of it like a weight being dropped. As it falls, its potential energy of position is transformed into the kinetic energy of motion. When it hits the ground, that energy is released as heat and sound. Now, imagine trillions of tons of diamonds sinking through a thick, viscous fluid mantle for millions of years. Each sinking crystal drags on the fluid around it, creating friction on a planetary scale. This friction generates heat. The diamond rain becomes a planet-wide heating system, a slow-burning furnace that constantly replenishes the world's internal warmth. This single process provides a stunningly elegant solution to one of the ice giant's most enduring mysteries, Neptune's thermal anomaly. Voyager 2 discovered that Neptune radiates more than 2.5 times the energy it receives from the distant Sun. It has a powerful internal heat source, but being smaller than Jupiter or Saturn, it was unclear where all that energy came from. The continuous slow settling of a vast diamond mass, releasing its potential energy as thermal energy, accounts beautifully for this excess warmth. It is the planet's hidden engine, stoked by a constant fuel of falling gems. This also casts the strangeness of its sibling Uranus in a new and fascinating light. Uniquely among the gas giants, Uranus is strangely cold. It radiates almost no excess heat at all, barely more than it gets from the Sun. Its interior appears eerily dormant. Why the dramatic difference? The diamond rain hypothesis offers a tantalizing, if unsettling, possibility. Perhaps the interior of Uranus is structured differently. Maybe there is a solid, stagnant layer within its mantle that prevents the diamonds from sinking all the way down, effectively switching off this internal heating mechanism. Or perhaps its convection is so sluggish, its inner dynamics so slow, that the heat generated by the falling diamonds is trapped deep within, unable to reach the surface layers where we can detect it. The phenomenon of diamond rain doesn't just explain why Neptune is warm, it provides us with a framework to ask precise, targeted questions about why Uranus is so cold. The presence, or absence, of this internal geological activity becomes a defining characteristic, a fork in the evolutionary road that sent these two otherwise similar worlds on vastly different paths. One planet hums with an inner fire fed by its carbon jewels. The other is a cold, quiet enigma, its internal engine perhaps stalled or frozen in time, but the influence of this diamond deluge extends far beyond simple thermodynamics. These sinking crystals are not falling through an empty void. They are massive, solid objects plunging through a dynamic fluid medium. As they descend, they don't just generate heat, they stir the pot. They create powerful, large-scale movements within the planetary mantle, dragging the surrounding fluid down with them in their wake. This process, a kind of diamond-driven convection, fundamentally alters the circulation of the entire planetary interior. Imagine dropping a handful of heavy stones into a thick, syrupy liquid. You would see currents and eddies form, a complex pattern of motion driven by the sinking weights. Now scale that up to a planet, where the stones are mountains of diamond and the syrup is a mantle of supersonic water thousands of kilometers deep. The diamond rain becomes the primary driver of vertical motion, the churning engine room that dictates how material and energy are transported from the deep interior back to the upper atmosphere. This constant slow-motion churn is the missing link, the crucial piece of the puzzle that finally allows us to understand the ice giant's most bizarre and defining feature, their magnetic fields. For decades, we have known that the magnetic fields of Uranus and Neptune are utterly strange. Unlike the neat, orderly fields of Earth, Jupiter, or Saturn, which are roughly aligned with their rotational axes, the fields of the ice giants are chaotic. They are tilted by huge angles, a staggering 59 degrees for Uranus, and are dramatically offset from the planet's physical centres. They are not simple north-south dipoles, but complex multipolar messes, with multiple north and south poles scattered across their surfaces. No conventional model of planetary dynamos could properly explain this profound weirdness. It was a ghost in the machine, an effect without a clear cause. The solution, we now believe, lies in the unique nature of the material being churned by the sinking diamonds. In the immense pressures of the mantle, ordinary water ice is transformed into an exotic state of matter called superionic water. In this phase, the oxygen atoms are locked into a solid crystal lattice, but the hydrogen nuclei, simple protons, are free to flow like a liquid through that lattice. A fluid of mobile electric charges is the essential ingredient for a magnetic dynamo. What was missing was the right kind of motion. A simple, uniform rotation of a planet is not enough to generate a complex field. You need convection. You need turbulent, chaotic, churning motion within that electrically conductive layer. And that is precisely what the diamond rain provides. The diamonds, sinking through the superionic water layer, create exactly the kind of complex, non-symmetrical and powerful convection currents needed to drive a dynamo. This is the grand synthesis. The diamond rain is not just a weather phenomenon, it is the celestial architect of the planet's invisible magnetic scaffolding. The irregular, deep-seated convection, stirred by the sinking diamond masses, generates a magnetic field in a relatively thin, conductive shell far above the core. This explains everything. It explains why the fields are not centered with the planet, because the dynamo action isn't happening in the core. It explains why they are tilted, because the convection is chaotic and not tied to the planet's axis of rotation. And it explains why they are so complex and multipolar, because the currents that power them are a turbulent, roiling mess, not a smooth, orderly flow. The diamonds in their long fall act as gravitational gyroscopes, twisting and warping the conductive fluid, generating a magnetic ghost that perfectly matches the one we have observed for 40 years. It is a stunning convergence of chemistry, physics, and planetary science, where the formation of the universe's most precious gem directly sculpts a planet's fundamental force field. This realization forces us to reevaluate what it means to be a planet. We tend to think of worlds as being defined by their surfaces, by their clouds, canyons, or craters. But here, the true character of Uranus and Neptune is being forged in their hidden depths, by a process we could never see directly. The diamond rain is a fundamental aspect of their being. It is as crucial to their identity as plate tectonics is to Earth's. It governs their thermal budget, drives their internal dynamics, and generates their protective magnetic shields. Without it, they would be entirely different worlds, likely colder, more stagnant, and with vastly weaker, simpler magnetic fields. The process is a core part of their planetary metabolism, a geological heartbeat measured in the slow, steady rhythm of sinking carbon. And the implications of this discovery ripple out far beyond the edge of our own solar system. For decades, we knew of only a few ice giants, our own too. But as our telescopes have turned to other stars, we have found that planets of this size and mass are not a rarity. In fact, they may be among the most common types of planets in the entire Milky Way galaxy. We have found thousands of sub-Neptunes and super-Neptunes orbiting other suns. These are the unsung workhorse planets of the cosmos. And if our understanding is correct, then what we are witnessing on Uranus and Neptune may not be an isolated curiosity. It could be a universal blueprint for a whole class of worlds. Across the galaxy, countless planets may be glittering in their hidden interiors with storms of falling diamonds. This process, this continuous cycle of carbon crystallization and descent, could be a fundamental factor in the evolution of billions of worlds. It would dictate their thermal histories, determining whether they cool quickly or retain their primordial heat for eons. It would influence their atmospheric dynamics, and most critically, it would be the primary mechanism for generating their magnetic fields. And a magnetic field is no small detail. It is a planet's first line of defense against harmful stellar winds and cosmic radiation, a crucial ingredient, many believe, for the development and survival of life. Suddenly, the question of whether an alien world has diamond rain is not just a geological curiosity. It could be directly linked to the question of its potential habitability. We have stumbled upon a fundamental planetary process that may be shaping the destinies of worlds across the void, silently determining which of them have the protection necessary to foster life, and which are left exposed to the fury of their stars. The fantastical image of a diamond storm has become a key metric in our search for our place among the stars, a clue to understanding the vast unseen diversity of worlds that populate the cosmic dark. And so, in that fleeting billionth of a second flash of impossibly bright X-rays, the case was closed. What we had just witnessed, contained within the diamond vice grip of a laboratory on Earth, was not merely an exotic chemical reaction. It was the confirmation of a new reality. It was the birth of a diamond forged not over geological eons in the belly of our world, but in the frantic, violent crucible of a distant planet's heart. For a brief, incandescent moment, we held the interior of Neptune in our hands, and it glittered. The journey that brought us here to this definitive, staggering conclusion stretches across decades of patient observation and audacious thought. It began with a pale blue-green dot, a ghostly whisper of a light in the eyepieces of our ancestors, so faint, so distant, that for centuries Uranus was mistaken for a simple star. Even after its discovery, it remained a featureless orb, a placid enigma. Neptune, its sibling in the outer dark, was no more forthcoming, a speck of deeper blue found not by chance, but by the subtle gravitational pull it exerted on Uranus, a phantom world discovered through the elegant language of mathematics before it was ever truly seen. These were the ice giants, remote, quiet, and cold. Also, we thought, our understanding was a sketch, a caricature drawn from a great and unforgiving distance. We saw them as simple, layered worlds of gas and ice, fundamentally static. But science is the art of revealing complexity where none was suspected, of finding dynamism in the seemingly inert. The truth, as it so often does in the cosmos, proved to be far more spectacular, far more violent, and far more beautiful than our initial timid imaginings. The reality is that these are not placid worlds at all. They are colossal chemical factories, planetary-scale engines of transformation. Deep within their swirling hydrogen and helium atmospheres, you descend into a realm where the very definitions of gas and liquid begin to dissolve. Here, under pressures 1,000,000 times greater than on Earth's surface, and at temperatures hotter than the Sun's photosphere, the fundamental laws of chemistry are rewritten. The simple methane molecule, a cornerstone of organic chemistry, a compound of 1 carbon atom and 4 hydrogen atoms, is subjected to a gravitational assault it cannot possibly withstand. It is ripped apart. The bonds that held it together for billions of years are shattered in an instant. The lightweight hydrogen atoms are liberated, free to rise through the dense, soupy mantle, while the heavier carbon atoms, now orphaned and alone, begin a new and extraordinary journey. Under this relentless, crushing pressure, they are forced to find each other in the gloom. They link together, forming intricate new structures, a cascade of crystalline perfection growing in the heart of a tempest. This is where the magic happens. This is the birth of the diamond rain. Solid, glittering crystals of pure carbon, precipitating out of the super-ionic fluid like snowflakes in a winter sky, but a sky thousands of degrees hot and under 1 billion atmospheres of pressure. They grow, perhaps to sizes that would dwarf any gem ever found on Earth, becoming hefty, solid projectiles in the planet's interior, and then, heavier than their surroundings, they begin to fall. Imagine a hail of diamonds, a perpetual silent storm sinking through thousands of kilometers of exotic, high-pressure fluid, a journey downwards that could take millions of years to complete. This process fundamentally redefines our entire conception of these planets. It is not a mere curiosity, it is a critical component of the engine that drives them. As these trillions of carats of diamonds sink towards the core, They release vast amounts of energy through a process of gravitational friction. Each falling crystal drags against the dense mantle, generating heat, a slow, persistent warming that emanates from the planet's deep interior. This elegant mechanism finally provides a compelling answer to a long-standing mystery: why Neptune radiates more than twice the energy it receives from the distant feeble sun. It isn't just leftover heat from its formation. It is being actively warmed, right now, by this incredible, ongoing precipitation of joules. The diamond rain is Neptune's internal furnace, its hidden powerhouse. For Uranus, lying on its side and mysteriously colder than it should be, this process hints at a more complex, perhaps layered or stalled, internal structure, a puzzle whose solution is now tantalizingly within our grasp. These worlds are not just cold repositories of gas, they're geologically active, their alchemical hearts transmuting the simplest of elements into the most precious of materials, and in doing so shaping their own destiny, generating their own climate and powering their own evolution. Reaching this profound understanding was never the work of a lone genius or a single discovery. It was a symphony of disciplines, a testament to the collaborative spirit that defines modern science, a conversation held across decades and continents between three distinct families of explorers. First came the observers, the patient sky watchers. Their story begins in earnest with the fleeting, audacious flyby of Voyager 2. For just a few precious hours in the late 1980s, humanity's robotic emissary gave us our first and only up-close portraits of these worlds. It revealed the bizarre, off-kilter magnetic fields, tumbling chaotically as if their source was not at the planet's centre, but in a strange, electrically conductive layer partway out. It measured the unexpected internal heat of Neptune and the baffling cold of Uranus. Voyager asked the profound questions, sketching the outlines of a grand mystery before plunging onward into interstellar space. In the decades that followed, the great terrestrial and orbital observatories took up the vigil. The Hubble Space Telescope, with its eagle eye high above the distortions of our atmosphere, tracked the faint ethereal auroras on Uranus, betraying the turmoil of its magnetic soul. On the mountaintops of Hawaii, the mighty Keck Observatory, armed with adaptive optics that pierced the veil of air, probed the deep atmospheric layers, tasting their chemical composition from billions of kilometers away. These observers provided the crucial constraints, the hard data points, the boundary conditions of the puzzle. They told us the what, the where, and the when, but they could not tell us the how or the why. For that, the torch was passed to the second family of explorers, the theoretical modelers. These are the architects of virtual worlds, the artists who paint with the laws of physics. Working in the silent humming halls of supercomputing centres, they took the sparse data from the observers and began to build Uranus and Neptune from the ground up, pixel by pixel, equation by equation. They simulated the crushing pressures and searing temperatures, playing out the fate of methane molecules under conditions that no earthbound vessel could ever visit. Their models were the first to suggest the incredible possibility of carbon splitting from hydrogen, the first to whisper the word diamond. They predicted that deep inside these planets must exist a strange transitional zone, a mantle of super-ionic water, ammonia, and methane, a perfect environment for this exotic chemistry to unfold. They hypothesized that the sinking of these diamonds could explain the heat, and that the strange, sloshing, electrically conductive ocean they fell through could be the very source of the off-kilter magnetic fields. It was a beautiful, compelling, and utterly coherent story. But it was still just that, a story, a ghost in the machine. To make it real, to give it substance, required the third and final family of pioneers, the experimental physicists. These are the builders of cosmic anvils, the scientists who have learned to replicate the hearts of planets, if only for a nanosecond. At facilities like the SLAC National Accelerator Laboratory, they unleashed some of the most powerful lasers ever conceived. They fired these celestial blowtorches at tiny, specially crafted targets of plastic, a stand-in for the methane-rich chemistry of the ice giants. The laser blast created a shockwave, a momentary spike of pressure and temperature that, for an infinitesimal sliver of time, perfectly mimicked the conditions 10,000 kilometers beneath the swirling clouds of Neptune, and in that instant, using the brilliant light of an X-ray free electron laser as a strobe, they watched. They saw the carbon atoms break free. They saw them squeeze together. They saw the unmistakable crystalline structure of diamond flash into existence. The theorists had dreamt it, and the experimentalists had built it. The observers, the modelers, and the experimentalists, each speaking a different scientific language, had come together to tell a single astonishing story. One group gazed out across the solar system, another gazed inward into the digital realm of a computer, and the third gazed into the microscopic heart of a laser-blasted target. From these three completely different perspectives, the same incredible image emerged, a world of falling diamonds. Yet for all its triumph, this discovery is not an end. It is a profound beginning. It is a gateway to a new era of planetary science, and it issues a clarion call for us to return to the outer darkness. Voyager 2 was a scout, a reconnaissance mission that flew past in a blur. What we need now is an inhabitant, a permanent robotic presence to orbit these enigmatic worlds and study them with the full power of 21st century technology. Missions are now being designed, drawn up on the blueprints of our newfound knowledge. Imagine a craft like the proposed Uranus orbiter and probe, a sophisticated explorer arriving after a decade-long journey across the void. This vessel would not merely glance at the planet, it would make it its home. For years it would circle Uranus, mapping its perplexing magnetic field with unprecedented precision, pinpointing the exact location and behaviour of the dynamo region that generates it. It would carry instruments that can analyse the subtle wobbles in its gravitational field, allowing us to infer the density and thickness of its internal layers, perhaps even detecting the massive settled layer of diamond that may blanket its rocky core. And this time, we would not just fly by, we would plunge in. The mission would deploy an atmospheric probe, a brave kamikaze packed with sensors, which would descend under its parachute into the planet's upper atmosphere. For one precious hour, it would taste the chemistry directly, measuring isotope ratios, tracking wind speeds, and sniffing out the chemical byproducts of that diamond formation process occurring far, far below. It would be a direct line of communication with the planet's interior, sending back its final secrets before being crushed and vaporized by the rising pressure. Such a mission would transform these worlds from distant points of light into living, breathing laboratories of planetary evolution. But the implications of this discovery resonate far beyond the orbits of Uranus and Neptune. They echo across the galaxy. In the last 3 decades, our telescopes have revealed a staggering truth. The cosmos is teeming with planets. We have found thousands of them, and we know there are billions, perhaps trillions more. And one of the most common types of planet we have found out there, the so-called sub-Neptunes or ice giants, are worlds that bear a striking resemblance to our own distant blue cousins. Before, when we would detect such a world orbiting a distant star, our models of its interior were simple, based on what little we knew. Now, everything has changed. The discovery of diamond rain provides us with a new, fundamental piece of physics to add to our models. When we see an exoplanet of a certain mass, a certain radius, and a certain chemical composition, we can now reasonably infer that it too may be an active diamond factory. We can predict that it may have its own internal heat source, its own bizarre magnetic field, its own unique atmospheric dynamics driven by this exotic process. The diamond seas of Uranus and Neptune are not a local curiosity. They are a potential universal truth, a common chapter in the story of planetary formation across the cosmos. It informs our search for life, as a planet's magnetic field and internal heat are critical factors in its potential habitability. What began as a question about 2 strange planets in our own backyard has become an essential tool for understanding the nature of countless worlds across the interstellar ocean. Our journey has taken us from the edge of our solar system to the heart of an atom, and then outward again to the farthest reaches of the galaxy. We have been reminded that the universe is not obligated to conform to our expectations. Its capacity for wonder is inexhaustible. It can take the most abundant elements, hydrogen and carbon, and under the right conditions of violence and pressure, it can forge the most beautiful and enduring substance we know. The same process that creates the delicate crystal in a ring on your finger, a symbol of permanence and light, is happening on a scale that defies comprehension in the turbulent eternal darkness of a world we can barely see. It is a powerful and humbling connection, a reminder that the laws of physics are a universal language, and that given enough time and the right ingredients, the cosmos will always find a way to build something breathtaking. The next time you look up into the clear night sky, past the moon, past the familiar lights of Mars and Jupiter, look deeper to the very edge of visibility. Know that out there, in that silent, frozen expanse, a storm of unimaginable grandeur is raging, a quiet, slow-motion tempest of falling jewels, a silent testament to the wild, creative, and utterly magnificent universe in which we are so fortunate to live.